Okay, we're going to look at mechanisms of heat transfer here. And you usually hear them listed in the order conduction, convection, radiation, because maybe that's the order that it's easiest to understand them in. But I'm going to do them in reverse order because we're going to study this one in some detail. And these two I'm just going to mention. Heat transfer is the way that energy is transferred from one thing or one place to another because of temperature differences between the two places or the two things. And so that's what we'll look at here. Radiation, this is energy that's given off by electromagnetic radiation. And this would be visible light, but it would also be light that goes all the way down to gamma rays at the very shortest wavelengths. And I'll list it short wavelength through higher wavelengths. Gamma rays, X-rays, ultraviolet light or ultraviolet radiation, visible light, and then infrared radiation, microwave, and radio waves. All of those things are electromagnetic radiation, and energy can be given off in those forms. Any object above absolute zero radiates energy through electromagnetic radiation. And in fact, you can think of absolute zero as being the place where an object would no longer radiate energy. Now, that doesn't mean it has none. It just means that an object at absolute zero has all of its components or all of its atoms, if you want to think of it that way, in their lowest possible energy states. And that's what it is. Anyway, for radiation, we can write down a number for it. And we'll be using the letter H for the rate at which energy is transferred. So H will equal dq dt as far as we're concerned. Q is the heat that might be transferred from one place to another, and dividing it by a dt makes it the rate of heat transfer. So we'll have that. And for radiation, it depends on the area of the object. So bigger objects can radiate more. Usually when we talk about the rate at which it's being given off, one of the things we'll be interested in is the intensity of the light coming from it, which is the power per unit area that's given off. But again, we're not going to be doing calculations with this. Something else that shows up in here is the Greek letter sigma. In this case, it stands for Boltzmann's constant. And for us, it's just a proportionality constant. It would have one value in the metric system, a different value in the imperial system, or whatever you choose to call the system that America is using right now. Although for most science, it's all metric anyway. So, and then a little letter here, E, for this stands for emissivity. And it's a measure of how efficient the object is at radiating energy. Some things are perfect radiators. We actually call those objects black bodies for reasons that are buried in history, but actually to the naked eye at ordinary temperatures, they will appear black and they'll be the blackest object you've ever seen, but they're also good at giving off radiation. So that's why that is. And then the important one that shows up in here is the temperature to the fourth power. And so this stuff has been well studied. It's especially important in astronomy. Excuse me for a minute. Especially important in astronomy, but that's as much as we're going to do with it. But it is kind of cool that it goes up with the fourth power of the temperature. Convection. This is one that we don't quite have the means to study very well in this class, but it's complex. And that's one thing you can say about it. Convection happens in liquids and gases, and It occurs when there is motion within the fluid or the gas, and warm things rise, cool things settle down, and they don't necessarily always have to be going up and down. You can have these currents of convection, and just an easy way to draw it, if you have a pan full of hot water, and you've got it hot down here because it's sitting on a burner, okay, you can have convection currents in there. In fact, this is an easy place to see it if you look close. There will be places where warm water is rising and then dropping down, and cooling when it reaches the surface and then dropping down. And that's what a convection current looks like. And they can be very complex. You can have all sorts of them going on at the same time. But if you stare at a pot of water that's sitting on a hot stove burner, you can start to see some of that kind of stuff. So that's about all I'm going to say to it, say about it, except, let's see, because of fluids having a viscosity, which is a resistance to flow or a resistance to move, you can usually have a surface film at the surface of something where there isn't any convection taking place. So, like if you've got air up here and maybe it's cold, and down here is some warm thing, there will be a small zone right near the surface of the thing. If you had a convection current right here, it would run into friction at the surface of this object, and there's less friction when you get above it. So here you might have convection currents with a small gap between them and the warm thing. And this is important for human beings. If you're outside and there's no wind, there will be a little bit of a zone near you that doesn't shed heat so well. It's like a thin insulating layer of air. And that little layer of air actually has about the insulating ability of about 1.3 centimeters of plywood, which isn't a whole lot, but it's better than nothing. And let's see, 1.3 centimeters of plywood would be about that much. So that's about what you'd have. However, if there's wind, that surface zone here can get broken up, the surface film. And so if there's a lot of wind or a strong wind, then it can vanish if that wind is strong enough. And so that's what wind chill is related to, is breaking up that surface film. Okay, that's enough on that. Now to conduction, which is the main topic that we'll be looking at. And here's what it depends on. We'll have dq dt showing up in there. We'll have a proportionality constant, K, and we're going to be dealing with this quite a bit. It's called the thermal conductivity of the material. So it depends on what type of material you have, and I'll show you a table of things here soon. Okay, and then it depends on the area of the object. So the bigger the object is, the more heat can be carried through conduction. And it depends on the temperature difference between the object on temperature on one side of the object and the temperature on the other side of the object. And I'll just write that as TH minus TC. And so we'll have that. And then it's inversely proportional on the length of the object. Heat will flow more slowly through a very thick layer than it flows through a thin layer. And that's a fairly easy idea to understand. But this is what all of it depends on. Now, as far as what those thermal conductivities might look like, first of all, their units are watts per meter Kelvin. The Kelvin is also on the denominator down here, so that's something that we have to keep track of. And the first things we have up here are a group of metals, and aluminum, 205, brass, blah, blah, blah. Copper is a good conductor of heat. Silver is a very good conductor of heat. A disadvantage of silver is it's kind of expensive. Gold is pretty good as well, but it's not as good as silver and copper. And then steel is down here a ways, and 50.2. It's not such a good conductor of heat, except things like steel have advantages because they're kind of sturdy. Here's a kind of an outline of a pan, and something you might have in cheap pans, they might just be a thin steel layer on the bottom, or even a thin aluminum layer for really cheap pans. They conduct heat well, but aluminum oxidizes. It isn't real sturdy like steel is. So a better way is to have a layer of steel. Stainless steel is nice on the inside of the pan and the outside of the pan. And then sandwiched between those layers of steel, have some aluminum that does a pretty good job of carrying heat, but is much more affected by corrosion and oxidation and stuff like that. Anyway, you have a tri-ply pan here, steel, and aluminum in the middle, and that's a pretty good pan, and you can make that aluminum layer thick. When you do that, you don't have spots on your pan that get really hot because of if there's a spot on your stove that's hotter than another spot in an aluminum pan, that'll kind of spread out, and so you get more even heating. So anyway, that's stuff that you think about when you're talking about thermal conductivity. Then there's a section for building material type things, insulating bricks. You can get red brick, concrete, cork, felt, fiberglass. This is like for insulation, and you can see it has a very low thermal conductivity here. Rock wool is another type of insulation. I sort of wish we'd had some rock wool for insulation in parts of our house, because this is pretty good at absorbing sound. And so if we'd had rock wool between the floors of our house, for instance, you wouldn't hear sound so well being transmitted from people walking upstairs or talking upstairs or downstairs, or a dog barking downstairs like I have right now. Styrofoam is pretty darn good. It's kind of creepy stuff environmentally, but it's a good insulator. And then wood has quite a range, depending on the species of the wood, how well dried it is, and lots of things like that. So, and then we've got gases, which we'll be talking about. Gases are not very good at all at transmitting heat. Let's see, oxygen, hydrogen, helium. Some of these are kind of, you're not exactly going to want to have them as an insulator. Helium would be expensive. Hydrogen, well, it's kind of flammable, you know, could be anyway. Ordinary air, 0.0262. Argon is better. And this is something that is starting to be used in filling windows. And so we've got an example problem where we'll use some argon. So let's dive into some problems and see what we can do with these. Okay. Prior to the 1970s, just about any house you bought would have had single pane windows. And in the 1970s, they started transitioning to dual pane windows, which have 2 panes of glass. And we'll look at one of those for a sample calculation. But a single pane of glass, let's just imagine this old house has a picture window, single pane of glass, 4.55 millimeters thick, and it has an area of 3.15 square meters. And I just kind of made up a sample window here. On a night when the temperature outside is 25.5 degrees Fahrenheit, which is minus 3.61 degrees Celsius, and the temperature inside the house is 61 or 16.1 degrees Celsius. And it's that cool because the occupants are trying to save money on their heating bill. Actually, we do that at our house. We turn the heat down starting at 9 p.m. We basically shut off the heat and have it drop down to 60 degrees Fahrenheit. Perfectly okay for sleeping in. And then at 6:45, we have it start back up and turn it back up to 65, which is what we have it set at during the day. And we're comfortable at those temperatures. Anyway, we're going to use this for the window glass, which is a value that was on the table that I had there. So here's the deal. We've got a place here where there's a thin pane of glass on the inside of it. It's got a temperature of 16.1 degrees Celsius. This is inside. Outside, we've got a temperature of minus 3.61 degrees Celsius, and we may as well just leave it at minus 3.61 degrees Celsius. And the heat is going to flow from inside of the house to the outside. So that's the direction of the Q flow. It goes from warm things to cool things. Okay, well, H in this case is going to be K times A times the temperature difference divided by the thickness of the glass. And if we just plug in all the numbers here, let's see, sometime yesterday I solved this problem or plugged in the numbers, but K is 0.96 watts per meter Kelvin. And I'm being really careful with the units. When you're starting to deal with things like this, you want to make sure that you're coming out correct. 3.15 meters squared for the area. Temperature difference in this case is 16.1 minus 3.61. Now, here's an important thing about temperature differences. They're the same whether you're on the Kelvin scale or the Celsius scale. And both of these are on the Celsius scale, but I can just call those things Kelvin because it's a temperature difference, and it'll be the same thing on either scale. And that's a 3.61. And then the thickness of the window is not very much. It's 4.55 times a millimeter is 10 to the minus third meters. Okay, let's check out the units. Kelvin here, Kelvin there, they divide out. Meter here, this is on the bottom, this is on the bottom. I've got meters squared on the bottom and meters squared on top. They all divide out. And so I end up with watts, which is what our unit of heat flow is going to be. In the American system, if you stuck with that all the way through, you'd end up with BTUs per hour. A BTU is a British thermal unit. But I think even in the building trades, they're starting to talk about watts and things like that, although they do use R values some as well. But if you calculate this, you get a rather large value. 13,100 watts is how much heat is flowing through that window. Okay, that's 13.1 kilowatts. Let's see, the kilowatt hour is about, let's see, I don't know, just wild guesstimate, 4 cents per kilowatt hour, something like that. So you've got 13 kilowatts. So every hour at night, they'd be losing about 52 cents or paying for 52 cents of energy, which may not sound like a lot, but it adds up, and that's only one window in the house. So kind of crazy. Now, you could do things to improve that. For instance, if you had curtains in front of your house, that gives you a layer of fabric insulation and then a larger dead air space, which isn't completely dead air. It's big enough to have convection currents in, but that would help. Anyway, there's a fairly large bill here. Now, two houses down is a house with an identical window. On the same night, the heat flow through their window is 18 kilowatts. What's the temperature inside the house? So here, everything is the same except the T sub H in the house is an unknown quantity. We know what the temperature outside is. We just have to figure out what the temperature inside is. So we can just set up an equation where this time we know H, it's 18 times 10 to the third watts. That's what a kilowatt is. And that'll equal K times A times TH minus TC over L. And I guess you can write the L underneath all that stuff. It doesn't really matter. But we rearrange terms here and solve for TH. Let's see, you'd have 18 times 10 to the third watts times L, which is 4.55 times 10 to the minus third meters. So you'd have watt meters on top, and the 10 to minus thirds would go away, and 10 to the plus third. And then on the bottom, we would divide by K and A. So 0.96 times, whoops, that's not times 10 to the anything, it's watts per meter Kelvin. And the area, 3.15 meters squared. And that would equal TH minus TC. I've moved everything else over, but I'll add the TC onto that, plus TC, and that'll be the temperature inside that warmer house. So how much is it going to be? Well, if you actually solve for it, oh, why did I do that? I'm not sure. I think I need to solve for it. Go ahead and plug in the numbers. Okay, and I get a temperature in the other house of about 24 degrees Celsius. So that's probably well, actually, that's pretty warm. Yeah, they're just blasting the heat out, 18 kilowatts. So anyway, that would start the cost and be kind of expensive. So let's see a more practical way to do this. And this would be something that, I don't know if thermopane is a copyrighted term or not, but what it is a window that has two layers of glass, each 4.55 millimeters thick, separated by an airspace of 5.00 millimeters. Now, you could improve this. Now, they've found that you can have an air gap of up to about half an inch in thermopane, half an inch, which would actually be about 13 millimeters, and that would make it even better. But let's just go ahead and solve for this window here. The inside is at 20 degrees Celsius, and the outside air is at minus 30 degrees Celsius. So let's see. they could, well, this might be during the day on a cold winter night, but it's a much larger temperature gap. This is a 50-degree temperature gap, and I should have put a 0.0 on this thing because I want to measure it more precisely anyway. So let's figure out the heat flow in this case. And it's going to be a bit more complicated. Let's see, if I draw a picture here of what's going on, got a layer of glass here, layer of glass here, and air here. And we've got heat flowing out of the house through the glass and the air gap and then into the outside. And so the heat flow, once this thing is in what we'd call a steady state, you have the same amount of heat going from the glass or from the room inside through the glass, through the air, and through this layer of glass again. So the heat flow is the same through all of those things. It may take a half an hour or so for it to reach a steady state, or just some amount of time, but it'll happen anyway. So that's what's going on. However, we've got a hot temperature in here. We've got the cold temperature out here, but we've got a couple of intermediate temperatures in here. And I'm going to call this one T, what did I call it when I solved this problem the first time? I think I called it T2 right here, and this would be T3 here. And so I need to set up three separate equations involving the heat flow, but they're all going to be the same. So first, I'll consider the heat flow through that first pane of glass, and that would be dq dt. Okay, but dq dt is the same everywhere, and it'll be the thickness of the glass times its area times pH minus T2. And then I divide by the thickness of the glass, which I'm going to use a T sub G for that. Okay. Oh, and I've got K sub G here for the thermal conductivity of the glass. Okay. Then we'll use the same thermal conductivity for the glass that we used last time. Then for 2, I'll consider the heat flow through the air gap. So H in that case is going to equal the thermal conductivity of air times the same area. The air gap between the windows is the same size as the window. And this time the temperature difference, TH minus TC, is going to be T2 minus T3. You'd expect the right at the inside surface of this first pane of glass to be warmer than the one that's the inside surface when it's up next to the cold temperature. So T2 will be greater than T3. And you could actually figure these out if you wanted to. And then this will be the thickness of the air gap, is what we have for that one. And then we'll have a third situation, H, third H, which is going to be, it's going to look just like this one, except we'll have different temperature differences. So we'll have KGA. This time it's going to be T3 minus TC. And on the bottom, we'll have the thickness of the glass again. So I don't know why I used an uppercase G on the bottom and a lowercase g on top, but I did. So anyway, they both stand for the glass. Well, this is kind of complicated. However, there's a way around it. And what I'm going to do is solve all three of these equations, or rearrange terms, so I just have the temperature differences on the right side. And so let's see what happens when we do that. Remember, H's are all the same. Well, I'm going to multiply out from underneath by the T sub G and divide by the K sub GA. So I'll have H times, in this case, T sub G over K sub G times the area. And that will equal TH minus T2. For the middle one, I'll have T sub air divided by K sub air times the area. And that will equal T2 minus T3. And maybe you're starting to imagine how I might solve this thing. And for the bottom one, I'll have H times T sub G over K sub G times A again, and that'll equal T3 minus T3, or TC, I mean. Okay, now if you can imagine how I would solve that, the way I'm going to solve it is to just add the left sides together and add the right sides together. When I add the right sides together, I've got a minus T2 and a plus T2. I've got a minus T3 and a plus T3. Those are going to add to 0, and I'll have TH minus TC. So over on my right side, I'll have TH minus TC. And I know both those temperatures and the unknown temperatures are gone. So the only things I've got left on the left side are things that I know. But let's go ahead and write this out here. I'll have H times this stuff, H times this stuff, and H times this stuff. I'm going to put the H's outside and just have these things all in parentheses here. So I'll have T sub G over K sub G A. In fact, I've got 2 of those for the 2 panes of glass. And then I'll also have T sub air over K sub air times A. Well, I just have to divide by this and I can solve this thing. I think what I'm going to do, though, is, well, go ahead and write this. If I divide both sides by this, I'll have T sub H minus T sub C on top. And on the bottom, I'll have 2 T sub G over K sub G plus T sub air. Whoops, there's also an A here. K sub air times A. And I can actually bring those A's up on top. They're common. I could factor out a 1 over A and then bring it up top. And so it would look like this. H equals A times T sub H minus T sub C. And then on the bottom, I've got these 2 T sub G's over K sub G plus the T sub air over K sub air. Now, because these things are down in the bottom, they are a measure of how the heat flow is being slowed by the glass and by the air. And I want to calculate those individually just because. And if I do those, I'd get, well, I'll just write in the numbers here, but for those ones, I'm going to calculate it. I've got the, hang on, let me put that down. Nothing I recognize. Anyway, 3.15 meters squared, TH minus TC, that's a 50 Celsius difference, 20 minus negative 30, but it's also 50 Kelvin, so 50.0 Kelvin. And then on the bottom, I want to calculate this number, and I'll just do it over here. 2 times the thickness of the glass is 4.55 times 10 to the minus third meters, and divide by the K for the glass, which I used it in the last one. I'm going to put it over in here anyway. 0.96, and it's watts per meter Kelvin. And actually, the Kelvin will come up on top, and what else will happen? The meters will go away, actually. Yeah, something like that anyway. But let's get the numbers first. 2 times. Okay, and for this, I would get 9 point, I've only got 2 sig figs, so 9.5 times 10 to the minus 3. And the units, I'd have Kelvin meters over, actually Kelvin meters squared per watt is what I have. So Kelvin meters squared per watt, which is a weird thing, but it's a measure of resistance to heat flow, actually, is what it happens to be. But it's in the bottom. So this one, 9.5 times 10 to the minus third Kelvin meters squared per watt. And you can see I've got Kelvin meters squared on top, so it's going to divide out. So that's for the 2 pieces of glass. Okay. Now for the air, I just take T for the air, which is, look up on my table here, 0.0262 watts per meter Kelvin. So 0.0262 watts per meter Kelvin. Whoops, that's what goes on bottom. I wanted the thickness of the air on top. Oh well, the thickness of the air was 5.00 millimeters. And if we calculate that, I get 1.91. Oops. Oh, I forgot that was a millimeter on top. Let's see. I get 0.19. Let's see, this one, I can keep 3 sig figs on it, actually. It's decimal point 0.191, and this would also be Kelvin meters squared per watt. Okay, so this is the resistance term on the bottom. Actually, in America, we'd use different units, but this would be called the R value. But something you can see is that this single layer of air is a lot bigger than that. In fact, if I divide 0.191 by 9.5 times 10 to the minus third, divided by, not times, this is 20 times as large as that. Okay. So almost all of the insulating value of that window is because of this air gap. And you could double this. You could make it 2.5 times as large. So if it was 2.5 times as large and not have to worry about convection currents still, you'd have something that was, this part would be 50 times better than that. And so that's amazing that you can improve it that much. But anyway, if we go ahead and finish off this calculation here. Okay, I get about, let's see, how many, actually this, when added to this, doesn't show up until you get over to this digit anyway. I can keep three significant figures here, and it's actually about 786 watts. So even though the temperature difference here is much more extreme, this is actually pretty darn cold. And you've got the same size window, but on that previous problem, we were talking about 13,000 watts or 18,000 watts for this one, and much more extreme temperatures, and we've only got 786 watts going through that window. And you could improve it a lot more. You could actually cut it down by divide this by 2.5 if you had a 12 millimeter, 12.5 millimeter air gap, and do a whole lot better. So you can be smarter with your windows. And nowadays you can't even buy a single pane window, I don't think, unless you go to some place that's taken a bunch of windows out of a house from an ancient house and they're selling them used, but they'd be 50-year-old windows by now. Anyway, there's another problem there. Okay, one last problem we can do here has to do with, this is a completely artificial situation, but it's just an example. We're going to figure out the temperature of this interface here and see how we might do it. We have a bar of gold in thermal contact with a bar of silver of the same length and area, and somewhere on my table of values, it didn't have gold, and so I had to look it up for this. And I was actually surprised to see that people have tested the conductivity or the thermal conductivity of metals at a wide range of temperatures. And for gold, I had to look one up for this is between 30 and 80 degrees Celsius, which is between about 303 and 353 Kelvin approximately. And there, the value for gold, and I'm going to use K sub AU for that, is equal to about 315. And that's watts per meter Kelvin. And for silver, K sub AG, let's see, aurorum in Latin meant shining dawn, and that's why gold got that. And I can't remember why silver gets an AG. It was for a Latin term anyway, whatever it was. And it's wherever it is, 406 watts per meter Kelvin. But we've got a problem to solve here. We've got another one of those things where this time we'll just have a heat flow through the gold and a heat flow through the silver, and they're both going to be the same. I'm going to have some intermediate temperature here, which I'm going to call T sub U for the unknown temperature, and that's the thing that we're after here. So for the heat flow through the gold, we'll have that H is equal to K for the gold times the area of the gold, which we're not given. So we're going to have to be clever about how we solve this thing. And then times, I'll call this T sub H and this T sub C. So I'll have T sub H minus T sub U, unknown temperature, and divide by the length of the gold. And it says a bar of silver of the same length and area, that's of the bar of gold. And so they both have the same area, they both have the same length, which we don't know, but maybe we can get away with not knowing them. But at any rate, I'll call each of their lengths L, and it said they're the same, so I can use that. So there it is for gold. For silver, it'll have the same heat flow through it. And when the heat flow reaches steady state, it says, so I'd have K sub AG times A times, this time it's TU minus TC. And let's see, over L again. Now, how can I solve for that? Well, in this case, I don't know TU, and I don't know A, and I don't know L, and I don't know H. So none of those things I can figure out. So let's get rid of them. Let's do this. Let's divide, well, actually, let's divide the top equation by the bottom one. Left side over left side, what's H over H? That's 1. So I'll have 1 is equal to K sub AU. Oh, I'll have A over A. Those are going to be gone. So I'll have K sub AU times TH minus TU. Scribble that out. Oh, and the L's will divide out also. Anything that's common, and this is all multiplication and division, so stuff just goes away. And then I'll have K sub AG times TU minus TC, and that's what I've got. Okay, well, that's not so bad anymore. Then I just multiply out from underneath by that, and I'll have KAG times TU minus TC equals KAU times TH minus TU. Well, that's not such a bad problem anymore. Okay, a little algebraic trick, dividing one equation by another. Okay, distribute to get rid of the parentheses. So K sub AG times TU minus K sub AG TC is going to equal K sub AUTH minus K sub AUTU. Okay, and oh, what can we do here? I guess get the TU's on one side. So I'll have K sub AG TU plus K sub AUTU is going to equal K sub AG TC plus K sub AUTH. Okay, so the temperature of that unknown thing is going to equal, if I factor it out of there and divide by that, I'll have K sub AG times TC plus K sub AU times TH. And I hope I didn't make any algebra mistakes. And then I've got the sum of the K's down here. So I'll end up with kind of a weighted average of these two temperatures, weighted by the chemistry thing. So if I actually plug in all the numbers here, oh, let's see. And I'm wondering if maybe, to be safe, I'm going to convert these to Kelvin temperatures. And to get Kelvin from Fahrenheit, you just add 273.1 to the Celsius temperature and you get the Kelvin temperature. So TH is going to equal this plus 80, which is going to be, it'd be 0.15, but we've only got significant figures to there. So it'd be 353 TH, 353.1 Kelvin, and add 30 to it, and TC is going to be 303.1 Kelvin. Okay, so just, I'm not positive that'll make a difference, but just to be on the safe side. Okay, so I look it up for AG. That was the one that was 406 watts per meter Kelvin times TC, which was 303.1 Kelvin, plus KAU, that was the one that was 315. And I just estimated that because I looked about halfway between this one temperature range that was in the table I looked up. Anyway, it's still watts per meter Kelvin. And that one's times 353.1 Kelvin. And divide by the sum of these two things. So 406 plus 315 is going to be 721 watts per meter Kelvin. And that unknown temperature, and I can first figure it out in Kelvin and then worry about it in the other stuff. And I get 325 Kelvin, which is minus 273. That's about 52 degrees Celsius. And so anyway, there we are. That's the final temperature of the junction. And it's in between 80 and 30, but not exactly in between, but not far off. So it's an average of the two temperatures, but it's a kind of weighted average here. It's weighted by their thermal conductivity. Okay, I'm going to stop there, and we have more problems, but those will be on the next lecture in this series.